Hello, everybody. Good afternoon. We're going to give the last class today on Neo4j on graph databases. So this is the last lecture of the course. We'll have a conclusion lecture later. And after this, we can dedicate the time of the classes to projects. So in terms of NoSQL, we already spoke about three different categories: key value stores, column families, and document databases. And the last category of family that we have to discuss today is the category of graph databases. So we see that graph databases are the most complex of these families, but also the least scalable. So somehow we have some more expressivity in terms of queries and so forth that we can answer with respect to graph databases than when compared with the other families of NoSQL. So there's been a lot of attention recently on graphs, lots of people talking about graphs and how graphs are useful for data management. And a lot of this is to do with, for example, Google Knowledge Graph. This idea of knowledge graphs has become popular, where various companies and organizations are using graphs as an abstraction to model diverse data at large scale. So this has also led, for example, to proposals of knowledge graphs by other companies. We also have, even before Google's knowledge graph, this Facebook Open Graph protocol, which allows people on the web to describe their data using graph-based formats. We have GraphQL released by Facebook, which is a new way of describing APIs for the web, which is actually not really related to graphs, but okay, it's got the name graph in it. We have graph databases being released, for example, by Amazon. Amazon Neptune is the name of Amazon's relatively new graph database, although it's been around for a few years now. And we see that it's a topic that has been increasing in popularity here with Google Trends. We see searches over time, and we see it has been growing in popularity. Still not quite as popular as relational databases, but at the same time, if we focus here, we see that it's becoming more and more popular. More and more companies and so forth are using graph databases. So what is a graph database? A graph database can take two, the most popular models used for graph databases are as follows. So the first one is the directed edge label graph model, where we have some nodes, we have some edges between these nodes, and these edges have labels. So for example, here we're describing some data about astronomy. And we see that we have this TRAPPIST-1, which is a star in the constellation Aquarius. Its child or planet around it is TRAPPIST-1b. Another one is TRAPPIST-1c. I think it has about 8 planets in total. So this was a star that was discovered in Chile, or using a telescope in Chile. We see some mass and so forth. So we represent data in this way with nodes and labeled directed edges. Yep. This can then allow us to do some queries. In this case, I have a query written in Sparkle. For those maybe who've taken the web of data before, this would be familiar. For those who haven't, this would be completely new. But what we're doing with this query, it might look a little bit as well like SQL, is we're writing a query against this graph where we're looking for astronomical bodies and what constellation they're in. And these are path queries here. So we'll talk a little bit more about this in another context, in the context of Neo4j a little bit later. A different model, an alternative to directed edge label graphs, is to use property graphs. So with property graphs, we have this structure here, where associated with nodes, we can also have properties and values. And associated with edges, we can also have these properties and values. Yep. So rather than having, for example, the mass represented as a node in the graph, we actually associate it as a value for a property on this larger node, or this node it's associated with. So property graphs, we additionally have labels on all nodes and edges, and we have labels on edges. So this is the property graph model, and then we have the directed edge label graph, where essentially we represent exactly the same information as before. So how does this work? Basically, in this case, we're representing exactly the same data. So there's nothing that a property graph can represent that a directed edge label graph could not represent, for example. So these are the two main models used in practice, and this is the property graph we'll use for the examples. So we have here, essentially, we have a social network where we have 3 people. We have Julie, John, and Frank. So Frank thinks that U2 sucks for some reason, and so does John. John knows Frank because John's brother is Frank. Julie knows John, John knows Julie, and Julie is following this tag about you too. Okay, so here we have this query, and we're going to have to discuss this in more detail. This is the query language we're going to discuss today, which is Neo4j. Neo4j's query language called Cypher. So what we're saying here is essentially we're looking for nodes that have the first name Julie, that have the tag person, that know recursively some other people. And then we're looking for the things that those people like that have a tag that is followed by Julie. And then we're returning the first name of this other person. So it's a fairly complex query. We'll have to come back to explain that in more detail a little bit later. So why do we need graph databases? Effectively, there's this push towards flexibility where we have very diverse data. And in very diverse data, if we try to use the traditional methodology of relational databases where we have tables and so forth, the problem is how do we create a relational schema for very diverse data? So if we wanted to create, for example, a relational schema to describe some very open domain where we don't know all of the entities and all of the relations, it would be very difficult to define a schema up front. So in the setting of, for example, banks and so forth, where relational databases where you have a relational schema that has certain tables for debit and credit and accounts and clients and exchange rates and so forth, this schema is unlikely to change very often. And relational databases are super good for this sort of scenario. Okay, so in this sort of scenario, everything works very well, and there's no reason not to use a relational database. However, if we're in other scenarios where we want to describe some data and we had no idea about what kinds of data we would like to describe, it could be more difficult. So if we want to describe, for example, a schema about planets, and we want to describe astronomical data, we can start by just naming some planets. And then we could maybe add some more information, for example, the distance of the planet from the in astronomical units, which would be relative to the distance of the Earth from the sun. And then we could continue completing these data and adding some information about radius, again, normalized by the size of the Earth. And then we could continue and fill out all of this astronomical data here until we have our planets. And we have information about gravity and days and years and temperature and rings, if they have rings or not. And the days here are negative because they go in the opposite direction of the revolution of the Earth. So we have some data about planets. Let's say now we decide we want to model some moons. Okay, so we add a new column and we say, okay, we add into our table a new column for moon. So this symbol here represents somehow a null, which means that there's no value. Okay, so these planets have no moons. So is this a good design for a relational schema? No. So we don't want to have these many values here. This would be 0 and f, and we don't want the 0 values here either, right? So essentially, this is a bad design. What would we normally do? We would take this and put it into another table, right? So we create a new table, which would be moon or natural satellite, if we wanted to use the technical term, because the moon is our moon, but okay. We have the name of the moon and we have the planet. Okay, so this allows us to represent 0 or many moons for every planet without any problems. So we're going to describe some discoverers and some years in which the moons were discovered, where we have nulls in this case again, because, for example, in the case of Luna, of our moon, who should we put as the discoverer or the year when the moon was discovered? So this doesn't really make sense, any values here. So if we wanted to normalize this, since they are optional columns, we should actually probably define different tables for those. So a moon discoverer and a moon discovery year. Okay. So what about in this case? We have a problem because we have this planet called Theta, and we see that the planet here, Theta, does not appear anywhere at all. So what do we need to do in this case? How do we avoid the situation in a database, in a relational database? With an ID. Yeah, so we would use something, a special ID called a primary key, a foreign key, sorry. So we would say that this column here is a foreign key that points to the name of the planet here. Yeah. So if we did this, if we define this foreign key here, then it means that we can't have names of planets that are not described in our primary table. Okay, so we're advancing. We have some sort of schema. Now we decide that, or somebody decides in 2006 that Pluto is no longer a planet for whatever reason. I guess there are lots of, if Pluto is a planet, then we'll have 25 planets, but okay. So Pluto is no longer a planet. What does this mean? What should we do to our table? Wait, so we could delete the row, right? So, but we think, okay, maybe we'd like to keep this interesting information and maybe we'll use it in the future. So what we do is create another table called dwarf planet, for example. Okay, but now we have a new problem, which is that if we look here in this column, we see we have Pluto, and Pluto is a reference to the planet table, and that Pluto is in the dwarf planet table. So what are we going to do? A join. So we could try to do something. So there's a couple of options. So the first option would be we could try to take a union of the tables as a view or something and say that it's a foreign key that points to a view, but that would be very strange. The second option would be to, instead of having one moon table, we have two moon tables. So we have moon of dwarf planet. Yeah, not very nice. And the third option, which is probably the more sensible here, well, it depends. One could argue for the different solutions, but we could say what we're going to do is we're going to remove the foreign key. So every time we come to these new situations, we have to change the schema. So now we want to represent exoplanets, where we have planets that are orbiting suns or stars that are not the sun, not our sun. So at this stage, we say, okay, we give up. This is just too painful. Okay. So in terms of graph database, how would this work? It's much more flexible. We start with the node, which is the Earth. We start with the sun. We connect this Earth to the sun. We think about what relation is between them and label the edge accordingly. Sorry. We continue adding new edges, new nodes, new edges, and continue growing our graph in this way. Yeah. So one thing is, when we're growing our graph, we should try to somehow use the same labels on edges. You know, we shouldn't try to invent new labels every time, but in general, it's much more flexible than what we saw before. So now we see that we have Pluto as an instance of planet, but we learn that Pluto is no longer a planet. What do? So we can just drop that edge, and if we wanted to, we can add a new edge. Yeah, instance of dwarf planet. We don't have to change the table. We don't have to change the attributes. We just add a new node to represent the type. And then if we wanted to represent exoplanets in different, in this case, it's not exoplanets, it's just the galaxy of the star, we can add the galaxy in this way. Okay, so in this way, we can continue expanding and growing our graph in a more flexible way that doesn't require us to maintain a schema at every step. Okay, so we can continue to grow the graph. So the pros and cons of relational databases, there's lots of advantages for relational databases. So the first advantage is that, or the first disadvantage is that we have to impose a structure or a schema from the start, which can be difficult, particularly when we don't have a fixed domain from the very start, where we might want to grow the kinds of data that we look at over time. And the con is that the pro is that we have a structure or schema imposed from the start. Yeah, so this is good because we know exactly what kinds of data we have. We can use the relational schema to explain what the data are and so forth. So there's more structure because it's imposed directly from the start. Yeah, so this is somehow like the commandments. It kind of forces you to follow some structure that you need to abide by when you're adding data, deleting data, and so forth. So it's a more rigid structure. In comparison with graph databases, the pros, we don't have to impose a structure or schema from the start, and you can probably guess the main con. The main disadvantage, that we don't have a structure or a schema imposed from the start. Yeah, so it's a trade-off. It's more flexible, but we're not following some high-level structure at every stage. So it's not that it has no structure, it's just that the structure is a bit more organic. It can evolve in a more natural way. Okay. So another reason why we need graph databases is for path queries. So for path queries, what I mean by this is the ability to query arbitrary length paths in a graph. So this is something that's not easy to do in relational databases. So for example, here, if we wanted to find astronomical bodies, that's fine, we can do that. But the problem is we see that there's no direct instance of astronomical body here. What we have are instances of subclasses of astronomical body. So in a relational database, we could, for example, join this with this to find an instance that is two subclasses away from astronomical body. Or in this case, we have an instance with 3, but in general, we can't easily query over arbitrary length paths. So in the case of graph databases, we can. So in this case, this pattern here says body with one instance, and then we follow 0 or many subclass to arrive to astronomical body, and we return those instances. So we can somehow do these graph queries. So in this case, we're counting essentially how many astronomical bodies there are in the Aquarius constellation, or whose parent is in the Aquarius constellation. This is this pattern here, where this says optionally 0 or 1 parent edge followed by a constellation edge. So here we see that TRAPPIST-1b, TRAPPIST-1, and TRAPPIST-1c will count. They're all counted as within Aquarius, and they're all instances of something that's recursively a subclass of astronomical body. And we can express these queries relatively straightforwardly in graph query languages. So if we look at the property graph here, we see a similar kind of query, but this time in the Cypher query language rather than Sparkle. And we have X1 as a person whose first name is Julie, who knows recursively some other people. And then we're looking for X2 likes something that has a tag that is followed by Julie. Okay. So if we look at Julie, we see, who does she know? Well, she knows John, right? But John knows Frank. So this star here says that we're going to also count Frank because it's recursively reachable. So in this star here in Cypher means 1 or more. Okay. But we know that Julie knows John, who knows Julie. Okay. So Julie also knows herself recursively. A little bit strange maybe, but okay. So we have Julie knows Julie, Julie knows John, Julie knows Frank. And this is all very good. And then we have to match this other thing here, that this other person that Julie knows has to like something. Okay, so John likes this and Frank likes this. That has a tag, okay, U2, that is followed by Julie. So we see that the results here would be, also Julie likes this as well. So Julie likes this, John likes this, and Frank likes this. So we should expect some answers, which is supposed to be a surprise for later. So we'll see the results later. Okay, so why specifically do we need property graphs? Why do we have this more elaborate model? So if we have a directed label graph, edge label graph like this, sometimes it might be convenient just to hang some information on an edge in particular, or sometimes a node. So in this case, the question is, how can we say that Galileo Galilei, whose node here, discovered Callisto and Io? Callisto is this moon here, and Io is this moon here, moons of Jupiter, I think, if I remember correctly, in 1610, while James Christie discovered Charon in 1978. I think Charon, yeah, is a moon of Pluto. Oh yeah, Jupiter here is mentioned. Okay, so what we'd like to do is add somehow the information of when this discovery happened, what year it happened in. Okay, so how would we do this in a directed edge label graph? What would we do? With a year? Yeah, so we would associate, we could put here maybe Charon and the year was discovered, right? Actually, that's a very good solution. So that's not the solution I have here. So because it's functional, you could do that. So we could also associate Callisto, a year discovered here, and Io because it's only discovered once, right? So in this case, what I'm going to do is a little bit unnecessary, actually, considering that solution is better. But here I'm going to create a node for the relation. So here I'm going to create a new node, which represents the discovery of Callisto, and then mentions what body was discovered, what year was discovered, and who the person was who discovered it. So this is a general pattern for this. But assuming that each moon is only discovered in 1 year, actually, you could connect it directly to the moon, or to one person, yeah. But if you connected it to the person, it wouldn't make sense if they discovered many things in different years, because you wouldn't know which thing they discovered in which year. But you could actually very directly just connect the moon to the year here. But in other cases, not the case. So the point with the property graphs is that what you'd like to do is just associate with the edge the year. Yeah, so you'd like to just say, wouldn't it be nice if you could simply just say here the year in which this edge held or began. So this is essentially the argument behind property graphs, where you have attributes on nodes and edges. So you can hang some information off an edge or off a node in order to describe that node. Yeah. And then we have some IDs on nodes and edges. So every edge and every node has a unique ID. And then we have labels on the nodes and edges, which are these post things here, or this likes that gives us a type, what kind of type of edge or what type of node it is. So there is some debate. This has become very popular, this property graphs. I'm not a huge fan of property graphs, but they have become very popular in practice. So I like the more minimal model, which is more than sufficient. But yeah, so this is popular, particularly in industry and Neo4j. Okay, so that's property graphs. So what are the graph databases that we can find in practice? If we look at our list of databases that we've seen a couple of times before, we look for graphs. We can start at the top and scan down along and scan down along, and we see that we get to our first graph system in position 22. So this is Neo4j. So 22 is maybe seems low, but it's 22 out of 400 and something. So it's still not too bad. Neo4j is quite widely known. So within just the graph databases, if we select these, we see we have Neo4j, we have Microsoft Azure Cosmos DB, which you can see I clicked because I have no idea what it is. But it's essentially this database that covers lots of different formats. And then we have Virtuoso, which is for RDF and Sparkle, ArangoDB, which is also another property graph style graph database, OrientDB, Amazon Neptune, and so forth. So we've got a long tail then of different graph databases. And we're going to talk about the most popular, which is Neo4j. Yeah. So Neo4j is a graph database. It is based on the property graphs model. It is using the query language Cypher. Its scripting language is Gremlin. And it has two licenses, open source on a single machine, and they sell a commercial edition, which allows you to distribute over multiple machines. In comparison with other NoSQL stores, it's not so easy to distribute graphs because it's not easy to know where to split graphs or how to partition them. But okay, so Cypher is the query language, the main query language for Neo4j. So we'll go through some features of that, which you'll be using in the lab on Wednesday. So we have match and return is the core thing. So what is match? Match allows you to basically specify a pattern that you want to match in the graph. And return tells you essentially your projection. What do you want to return as results? So Cypher has this syntax, which is kind of like ASCII art, where it uses round parentheses for nodes. And we'll see the edges soon. So it tries to draw the graph pattern that you want to match. X here is a variable and post is a label. So what essentially this is saying is, give me all of the nodes where it has the label post. Yeah, okay. So in this case, we will expect how many results? We would expect one result. Yeah. So we get one result, which represents the node here, N4, which is the only one with label post, and we get its properties and so forth. Yep. Okay, so this time we're going to match person and we're going to project an attribute of the node. So we're going to match nodes with label person, and we see there are 3 of those. And we're going to get their first names. So we get Julie, Jean, and Frank. That's relatively, hopefully, intuitive. So what happens if we extend this a little bit? We can also match a node that has gender male and has last name Cook. So we look here, we say this is label person, gender male, last name Cook. Person, gender male, last name Cook. So we'll return their first names and we get John and Frank. Yeah.
The printing of those, the return, it comes in order according to the node?
No, so the order here, if we don't specify it, we can specify with an order by command later, that we'll see. But by default, there's no deterministic order. So what will usually happen in these systems is they have indexed or stored the data in a certain order, and they'll just read out whatever order that's
so
it.
Doesn't change every iteration.
The order, no, the order of the results here, it shouldn't.
Oh.
Yeah, it shouldn't. But the order here doesn't really have any strong meaning. Yeah, no strong semantics. But you can order, which we'll see later. Yeah. Okay, so here we have the first names of the male cooks. Now we're returning person, and this time we're projecting first name and gender. So there is an issue here, which is that in the case of Julie, we don't have a gender specified. So it's, as we see before, it doesn't matter. The projection doesn't affect the selection. So we decide that we return all 3 nodes, and then we do not return, we just leave a blank element for the gender of Julie. Okay, so in this case, we're returning everything, all nodes, not of any label or anything, and we're returning first name, gender. So any idea how many results we'll get?
The quantity of nodes, the number of nodes.
Yeah, the number of rows. Yeah, so 5. Yeah. So we have 5 nodes, so we'll get 5 results. Yeah, exactly. So we see for the last 2 results, we just get blank because neither of them, there's no first name and no gender here. Okay. So in this case, we see how we draw edges. This is sort of ASCII art. You have to imagine that this is somehow drawing an edge between 2 nodes, a directed edge from this node to that node. So what we're looking for is X here, and we're looking for first name X. So what is X? These nodes will be matched by any node that has some link from a person node, from a node link person. So if we look at Julie here, we see that there is a link from a node labeled person. If we look at John here, we see that there's also one. And if we look at Frank here, we see that there's also one. Yeah. So we'll get all three first names of people. Yeah. So every person here has a link, some link with some label, doesn't matter. We haven't specified it from a person. Okay. What if we switch the direction? So now we're looking for the X person here that links to a person, right? So Julie, still fine. John is still fine. John links to Julie, Julie links to John. What about Frank? Frank, no. Yeah, so we get 2 answers here. So in this case, we get John twice because John has a link here and John has a link here, and we apply bag semantics. So we don't get Frank anymore, but we do get John twice, just representing the fact that there are 2 edges that satisfy this for John. So the multiplicity of the results corresponds to the number of matches that satisfy the reason why it's there.
So we have to specify to want the unique value.
Yep, and that would be with distinct, yeah. So which I guess might be the next slide if I remember. No, okay. I'm sure it'll come up later. So we would put return distinct and then we'll get a unique value. Yeah. For this case here, if we do X person and then we just do has some outgoing edge, then we'll get, how many times will we get Julie? We'll get 1, 2, yeah. And John will be 1, 2, 3, and Frank once. Yeah. So basically we get them for the number of matches or the degree of the nodes. Yeah, so here it is. So if we want to get rid of the duplicates, we specify distinct, and that gets rid of all the duplicates. Yeah. So this is set semantics. Okay, in this case, we're looking for people that know other people, so X1 and X2, and we're looking for the pairs. So X1 first name, X2. So in this case, we'd get Julie knows John, John knows Frank, and John knows Julie. Yeah, so we expect 3 answers, I guess. Okay. So we're going to make this a little bit more complex, and actually what we can do is also return the information about how they're connected. So we can find out what is the connection between these people. So in this case, or is a variable, and it's put in these square parentheses here to represent a label on an edge or a relation. And we have here or, and then we do or.rel. So we see that here, in this case, there's no such information, but here we see that there's the relation brother. Okay? So when we run this, we get not just the pairs of people, but we can also get how they know each other if that information is specified. For example, here that John knows Frank because they're brothers. Okay, if we return just the or here, what does it look like? It looks like as if something like similar as if it were a node. So the syntax is a little bit different because we use these square brackets, but we'll get the label of the relation, and we'll also get any attributes and values that might be associated with that edge if there are any. Okay, so in this case, we have y knows 2 things. So we have y knows some node and y knows some node. So we see we can draw the thing in either direction. So y knows some node here and y knows some node here. And then we want to return the first name. Okay, so in this case, we'll definitely get John because John knows Julie and John knows Frank. Yeah. Yeah, so that's the question. So it depends on what semantics we apply, because if we apply a homomorphism semantics or a graph homomorphism here, what it means is that we can send this node here to John, for example, and this node here to John to say Julie knows John, Julie knows John. So it's sort of like we put John here and we put the same node here, and then it satisfies the graph. So the question is, can we send, multiple query nodes to one node in the data? And the answer is yes. So we will not, however, match the same edge twice. So we can send the same thing to John, but we can't actually use the same edge here multiple times in the same query. So it's kind of like isomorphism, but it's a weird edge-only isomorphism. I don't know. So in this case, Julie knows John. Julie knows John does not count because we'd have to use this edge twice. John knows Julie. John knows Julie. This doesn't work either because we'd have to use this edge twice. So the only answer would be, and John Frank doesn't work. So the only answer is John, and it will be appear twice. It will appear twice because we can use Julie Frank or Frank Julie. So in one result, this is Julie, this is Frank. In another result, this is Frank, and this is Julie. Yeah. Okay. So we can match the same node twice, as I mentioned before. So in this case, we have the direction of this edge has changed. So we're looking for things that are known and that know something. Yeah. So we want an incoming nose edge and then an outgoing nose edge rather than two outgoing nose edges. So Julie is known. So there's an incoming nose to Julie, and Julie knows. So Julie fits, right? So we'll return Julie. John knows Julie, and Julie knows John. So that also fits, thinking that we can match the same node twice. So it's okay if we go John to John because we're not using the same edge. We're using two different edges. Even if we arrive to the same node, it's okay. Yeah. So for John to Frank, Frank does not know anybody, so we get nothing for that. So in this case, we get Julie, John, and John. So we get John twice because one result is from E2 to from E1 to E2, and another result is from E1 to E6. Yeah. So these are the two results for John. Okay. So person, some connection to some node, some connection to some node, some connection to X. Okay, so we're looping back. So first of all, X is a person, and then we need to find that it's connected to some node that's connected to some node that's connected to X with these directed edges here, and then get the first name. So what do we think? Would John work?
John? Yes.
John goes to Frank. I'm not sure. I'd have to check myself. So, okay, John goes to Frank, goes to U2, but there's no way back to John. But John likes this post, goes to U2, goes to, I don't see any way for John to work. I'm not sure. Yeah, I think so you have to find two nodes and then get back to John. So this one.
Would work, but it would return no.
4, 5. No, I think in this case, no, it will. Yeah, let's go back to the same person. Yeah. So in this case, there's 1, 2, 3. I mean, if you had 4 or 5, yeah. So John, I think no, there's no. Frank. So Frank 1, 2, no. So there's no way for Frank either. Julie goes to N4.
Yeah.
And 3 and yeah. So that one seems fine. Okay. Is there another one? Julie goes to John. John goes to no, but this direction is not good. Yeah. So there's only one way, and that would be Julie. Yeah. So Julie. So we're going from X back to X via 2 intermediate nodes with directed edges, with a directed cycle. Okay. As you can imagine, these queries can get complex. These can be difficult to evaluate. So this is, well, it's a similar cost to SQL. Essentially, you could represent this as joins in a relational database, but we're computing graph homomorphisms or something like isomorphisms, homomorphisms. So yeah, this can get a little bit costly depending on the complexity of the query. So in this case, we're just displaying as, so we can also rename the columns if we don't want to have it as displayed as first name. We can just display N1 and 2, for example, name 1, name 2 with the as in the return. If we wanted to match the same edge multiple times, there is a trick where if we do 2 matches, we're going to do the natural join of all of the matches. So for some reason, we wanted to do this query again, but we wanted to be able to match multiple times the same edge. We could rather break it into 2, rather than give this pattern here in 1 match, we can give 2 matches that compute a join between the 2. So within each match, we'll only match each edge once. but this way we can match the same edge multiple times. So in this case, x1 likes y and y likes x2. Before we had ruled out the possibility that x1, for example, could map to Julie, John, Julie, or Julie, John going back through the same edge, Julie. But now we can get these sorts of results. So we get Julie, John. We got John, Julie. So we can essentially go forward and back across the edges multiple times, and that gives us a number more of results. So we get more results than before. So let's have a look at this. So yeah, we see Julie, Julie, for example. So what this means is that x1 likes y, likes John, and y has to go back. We have to go back through E1 to get back to Julie. And here we see Julie, Julie. Okay.
Because it's likes, the match, it's about likes. So we can use those.
Sorry. Very good point.
The repetition happens because you do the same thing twice. I mean,
yeah.
She likes it, and
then you go back. Yeah, sorry, exactly. So this previous one was likes as well.
Yes.
They like the same thing. Yes. Okay, I missed that. Sorry. So thanks for that. Yeah. So okay, this one is relatively clear, anyways. We have as, but sorry, this is likes. Yeah, but this allows us then to go forward and back on the same edge. So Julie likes this post N4, and N4 is liked by Julie. So we can use this E5 edge twice, and that gives us the Julie possibility. And since everybody here likes this post, essentially we're going to get 9 results, right? So we'll get Julie, 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 John, John, Julie, Frank, John, Julie, John, 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 Frank, Frank, Julie, Frank, John, Frank, Frank. Yeah. Okay. Okay. So another important part of graph databases and graph query languages is the ability to match arbitrary length paths. So in this case, we have this in Cypher. We also have it in Sparkle. We have it in multiple graph query languages. So what does this mean? In Cypher, what we're allowed to do is to use this star or asterisk to denote that we want recursive paths following those. So this will match paths of length 1 or more. In Sparkle, just in case this is 0 or more, in case people have seen this in Web of Data or some other course. In the case of Cypher, it's 1 or more. So we can change that later, which we'll see. But so we're going to match arbitrary length paths of nose. So what we're looking for is x1 knows x2. Okay. So for example, for Julie, we can find John. But since John also knows Frank, we can go from Julie to John to Frank. So we're going to connect Julie and Frank with this path. Yeah. Okay. So here are all of the results. So we get Julie, John. We get Julie, Frank. We also get Julie, Julie. Why do we get Julie, Julie?
E1 and E2.
Yeah, exactly. So we go forward in E1 and we go back to E2. So Julie knows herself recursively. Yeah. Then for John, we have John, Frank, of course. We have John, Julie, and we have John, John. And the John, John is the same thing. No, we go forward from E2 and we go back through E1. Yeah. And then for Frank, Frank doesn't know anybody. So we're done. So here's an interesting one. John, Frank appears twice. Why does it appear twice? So we have the John, Frank through E6, but we have another result. E2, E1, E6. Still haven't used any edge twice. So that's also another valid result. Yeah. So yeah, so these are paths. We have a few options for how to match paths. So yeah, just to again mention that as in the match, we can't use the same edge more than once in a match. Which I'm not sure I like so much. I'd rather, if I wanted to, I would filter it later, but in any case, it's okay. So in this case, in the case of paths, however, if we were allowed to visit each edge more than once, we need some sort of restriction here. Because if we had no restriction on the paths, then we would, how many times could we return Julie, right? So we could return Julie, Julie once because it would go to E1, E2. But what about the path that is E1, E2, E1, E2, and the path E1, E2, E1, E2, E1, E2, right? So we need some way to restrict the infinite paths here. So what Cypher defines is that we visit each edge at most once. A more common way to do this is to say that if we have an arbitrary length path, that we shouldn't visit the same node twice. Yeah, in one path, in one single path. But in the case of Cypher, it defines that we visit each edge at most once. So that blocks these infinite paths around. Okay. So in terms of paths, we also have a few other options that we can choose. So we can, for example, set a minimum length of path. So we want to say how many edges here are traversed. So what this states here is that we are going to look for nodes, paths where of length at least 3. Yes, so we want to traverse at least 3 edges. So I think we saw one earlier, no, which was John, Julie, John, Frank, right? So that's, we go E2, E1, E6. Yeah, so that's length 3. Is there any others? Are there any others? I don't think so, no. So I think that would be the only answer. So yeah, we get from John to Frank. So we get to John to Frank, from John to Frank through E2, E1, E6. We can also specify a minimum or a range of path length. In this case, we're saying, give me all the paths of length 2 or 3, effectively. So paths of length 2, we have quite a lot more, right? So we have Julie, Frank, E1, E6. We have E1, E2. We have E2, E1. And then we also allow 3. So we get the E2, E1, E6. Yeah. So we get, sorry? Four results in total. Yeah, exactly. So we get these 4. Okay. Our maximum path length, which says that we want paths of length up to 2. So paths of length 1, 1 or 2. Yeah. So Julie, John, John, Frank, John, Julie, Julie, Frank. That's 4. Julie, Julie, John, John, 5, 6. 6. Yeah, we get 6 results. Okay. So we can also do something interesting here, which is we can specify the 0 length path. We can say that we want the 0 length paths. What are they? They essentially match a node to itself. So a 0 length path from N4 to N4 is it has no, you don't need any loop, you don't need any explicit edge. It's just assume that every node is connected to itself by 0 length path. It's related to, if you've done automata, this epsilon thing. It's kind of like a step where you don't actually read anything. You just move from one state to another in automata. But essentially, it allows you to go from a node to a node, from one node, from node N4, for example, back to N4 for free. So this is the 0 length path, which is the node itself, and will match any node. So what does this mean? It means that for X1 nodes length 0 to 1, X2, we'll get all of the 1 length nodes relations. So we'll get Julie, John, John, Frank, and all this. And we'll also get all nodes. Yeah. So we'll get essentially X1 will have to be equal to X2 here, right? But otherwise we'll get also results for all of the nodes. So we should get in total 1, 2, 3 plus 5, I think. Yeah. So we should get 8 results. So here we get the 8 results. So we get Julie, John. So we get Julie, Julie in the 0 length path. We get John, John. We get Frank, Frank. We get Julie, John because of the 1 length path. John, Julie for the 1 length path, and John, Frank for the 1 length path. And then we get blank results for these because they have no first names. Okay. So we get 2 blank results, one for this node here and another for this node here.
Do we have to specify the 0?
In this case, yeah. In other languages, there's in Sparkle, it's actually by default it has the 0. And in theoretical, in more theoretical or in the literature, it's most common that this star, which is known as clean star, it counts the 0 case. Yep. But in this case, no.
The class is 1 or more.
Yeah, 1 or more in Sparkle. Yeah. So in this case, it's 1 or more. This star, which is not typical, but yeah, that's how they define it. Yeah. So if you want the 0 length path, you need to say so explicitly. And I'm actually not sure even if it's possible to Yeah, I think you could. I think you can omit the you could just say that the minimum is yeah. So it would just be if you didn't want to give an upper length, you just write asterisk 0 and then nothing after it, and that means that it's the 0 or more variant. Okay, so here we get our results again. So we can also return paths from Cypher. We can return paths by setting, for example, p equals to this thing here, and this is a path expression, and then we can return the path itself. So what this will give us is very difficult to put it all in one part, but we have essentially the sequence of nodes, the edge, the node, the edge, the node, and so forth. If we try to zoom in a little bit just by soft wrapping it, this is what it looks like. So we have person, first name John, knows person, first name Shuli, knows person, first name John, knows with relation brother, person Frank. So we'll return as this sort of thing that gives us all the information of the nodes and the edges that form the path. So this can return a full path. What we'll do just to keep things a little bit neater here is we'll just give the IDs of the nodes and the edges that conform the path. So in this case, we have a path N2 followed E2 to N1, E1 to N2, E6 to N5, and we see that we never repeat an edge here, E2, E1, E6. So we'll use this in the slides. It's a little bit more concise, but in practice, your output will actually look like this, just to keep that in mind.
So we can get just the ID?
No, you would not get the ID, just the ID. I actually don't know of a way to do that. The problem is once you get this path here, this path syntax is very specific. It doesn't exist anywhere else. It's like you have a table that has this path thing in it, and you can apply specific functions on this, but you can't apply the algebra of the query language. You know what I mean? You have built-in functions that allow you to do things, and I don't think there's one that would just get you the IDs. Maybe I'm wrong though, because there's a lot of functions and a lot of expressions, but I don't think so. Yeah, so this is what we get. And in general, just to mention that Cypher, these IDs tend to be internal. You don't really tend to be returned those IDs. They're used internally for joins and so forth, but they're rarely, if ever, surfaced. I'm not even sure. I'm trying to think. Maybe you can't even surface them at all in the results, these internal IDs. So the N3, for example, or E3. I'm not sure you can get those out of the results. I'm trying to think. I'd have to check that to be sure, but I think they're generally not shown in results. Of course, you could explicitly store ID here as a property if you wanted. But yeah, so we can return a full path. Okay, so in this case, if we're returning paths, the issue is that we could again, return lots of paths, right? We could have very many paths, and it could be complex to compute. Okay, so in this case, we can specify different semantics for what paths to return. So in this case, what we're returning is the shortest path from Frank F to Julie, effectively, right? So from Frank to Julie, we see the shortest path. We see actually there's some options, but in this case, we just have shortest path. So we'll return any shortest path. Essentially, it's going to be the first thing it finds with breadth first search. Yeah, whatever is the first shortest path is found will be returned. Let's assume in this case, it happens to be, this is an undirected path as well. There's no arrow here, so we can go backwards or forwards and edges. So we'll assume here that the first one we find is N5, E6, N2, E1 or E2. It says E2, N1. Yeah, so we get the shortest path. So we get any shortest path, whatever is the first one to find. If we wanted to get all of the shortest paths, we could call all shortest paths, and then we'll get all the shortest paths matching the criteria specified. So we know that the shortest path has two edges. We already found one that was N5, E6, N2, E2, and 1. Any other shortest paths? Any other ideas? Yeah, so we could go likes with the post. So we go like N5 or N2, E7. I think this is directed actually. Yeah, okay, well, it's from Frank to Julie. Yeah, so we go N5, E8, N4, E7, and 2. We should also get the paths in the other direction. I'm not sure I represented those. Yeah, anyways, I think that's we'd actually get 6 here, but okay. So what we have here is the path from Frank to Julie via N5, E6, N2, E1, N1, the same path, but taking E2 instead of E1, and the one via likes where we go N5, E8, N4, E7, and 2. No, sorry, Julie. N5, E8, N4, E5, N1. Sorry. Yeah, this one here. What I think we should get as well, I'm just looking at this, I'm pretty sure we should get also all of the inverse paths.
No, because the order.
So F is on the left here, but this thing here is unordered. There's no direction on this edge. So it means that there's no difference between, I mean, you could start from Julie and take the exact path backwards and get a path of the same length. So I'm starting to think that probably this should include as well 6 paths. I can have a look at that and see and fix that, correct that if necessary. Okay, so in this case we have shortest paths, but this time we have direction. So now it matters that we're going from Frank to Julie. So in this case we need to go in the forward direction of the edges from Frank. So we need to go from Frank, we have no other option, to N4, and from N4 we have no other option but to go to N3, and from N3 no other option but to go to N1, and we're at Julie. Yeah. So the shortest path in this case would be a path of length 3, N5, E8, N4, E4, N3, E3, N1. In this case, yeah. So we return this path, and all is good. In this case, we have not just one node that we're going to match here, but we're going to match multiple nodes, because here we have Cook, that will match N2 and N5. And for C2, we have Freud, which will match N1. So the point here being that what does shortest path mean in this case for C1, C2? Is it the shortest over all the options of nodes, or how does this work? And it works by taking every pair of nodes and then returning for that pair of nodes the shortest path, right?
You return the shortest path for each node.
Yeah, exactly. So the shortest path here, if we were to consider over all nodes, would be John, Julie, and we'll just ignore Frank, right? But in this case, we'll actually, for each pair of nodes, which would be John, Julie, and Frank, Julie, we will return one shortest path. Yeah. So in the case of, and it's directed. So in the case of John, Julie, it's just the nos relation here. In the case of Frank, it's likes E8, N4, E4, N3, E3, N1. As before. So we get a response for each pair of matching nodes. Okay, any questions or doubts? Or in Zoom, any questions? Good. So that's the core of the Cypher query language. Then we have some functions for where to do selections or more advanced selection options. So we have your typical Boolean connectives. We have inequalities. We have an exists attribute property to see if if there is a property with some value. We have some string functions here. I don't know why it says Boolean, but string functions. So we have starts with, ends with, contains, and then a regex. We can see if a string matches some regular expression. So to take some examples, we add now this where clause here, where we can specify selection criteria on our graph. Yeah. So on the results that we return. So in this case, we have X likes some post, and we want to return X first name, but we want to make sure that the date of the relation, the likes relation, is between 2010 and the start of 2014. Sorry, the end of 2014. So if we look at our query here, we see that this likes relation here seems to be okay. Seems to match our where. So we would return the first name. We would return John for this. We see that this likes relation here is too late. So we ignore this one. And we see that this likes relation here is also too late. So we'll just get one result, which will be John. In this case, we see if we want to return nodes where there exists a value for gender associated with that node. So we see that we'll get results for John and for Frank, but not for Julie, because there's no gender associated specified for Julie. It starts with J. So we take the first name, we check all the first names that start with J. We see John and Julie, and we return those two first names. In this case, a regular expression where we're looking for names that have 0 or more characters and then have some number. Yeah, so basically this regular expression would match strings that end in some number between 0 and 9. So in this case, we look through here, we see not very much, but we see here that the name of this tag is U2. So we return U2 as a result for this. Okay, so in terms of ordering, if we want to order things, we have some, some features from SQL, which I'll go over briefly because we've seen them many times. If we want to order, we can order by a number of columns. So in this case, by content, then by date descending. So content ascending, date descending, skip 1 result, limit 1. So this would return the second element in the order. And in this case, we'll get this result here. So we take this, we specify what to return, and then we specify how to order and how to slice those results. We can also do an optional match if we want to do a left join in our graph. We can specify an optional match. So in this case, we're looking for x1 knows x2, and then we're looking for y has follower x1. Yeah. So we're interested in people who know somebody, at least somebody, and that person we want to know if they follow some tag or some topic. Yeah. So Julie knows John, so Julie is a result, and if she follows some tag, give me the name of the tag as well, and we see that she follows U2, so we'll return U2. John knows somebody, so John is going to be a result, and we see that John has no incoming has follower link, so there's nothing to return. It'll be none. Yeah. For Frank knows nobody, so not a result. So we see Julie U2, and we see John twice because John has 2 knows relations coming out. Okay. So it acts like a left join. We also see some relational operators like a union, where we can take results. In this case, x1 knows x2, x1 return first name. X1 knows x2, x1 first name, x1 knows x2, x2 first name. So we're looking for people that are known or that know somebody. Yeah. So in this case, it won't return a result for us because as in SQL, the columns have to have the same name. And here we have one thing called x1 and another thing called x2 first name, which it doesn't like. So Cypher will tell us, no, that's not okay. So column names have to be the same in the union, much like in SQL. So what we would have to do, in this case, the easy solution, we could also use as, but yeah, we just swap the 2 variables. And then union will apply a set union. So we'll just get each result once. If we wanted to do it, how would we do it in SQL? If we want to return duplicates, it's called union all. Yeah, so we can apply union all as well, and we get the same thing as we would expect from SQL. We preserve the duplicity of the results. Okay, so another feature, but it works a bit differently in Cypher, is the aggregation feature. So we can do things like count and max min and average and percentile and standard deviation and so forth. So what works a bit differently is that we don't actually group by. We don't specify any explicit group by. Rather, we will apply group by implicitly on the non-aggregated columns, which is an interesting feature. I'm not sure if I like it or I don't like it, but it's definitely, it's got an elegance to it. So what does this mean? It means that basically here we're returning the first name and count x2. So what it means is that we're going to group by the thing that's not aggregated. We're going to group by first name. Yeah. So we don't need to explicitly say group by first name and then select count something, right? So in this case, if we group by first name and we're doing x1 knows x2, so how many times somebody is known effectively, it will tell us.
How many people they know? How many people they know?
No, I think how many people know them recursively. So it's the x2 one here where, oh no, sorry. Yeah, it's true. It's x1 first name. It's how many people they know recursively. Exactly. Sorry. So you're right. So Julie would know John and Frank and Julie. So it would be Julie 3, right? And then John would know Frank, John, and Julie. So 3. And Frank is 0 or doesn't appear. Yeah.
Will not be a result.
Yeah, he'll be missing from the results. So we'll get Julie 3 and John 3. John 4. Why John 4? Well, it's not count distinct, so we'll have John knows himself. No, John knows Frank in 2 different ways. And since we don't have a distinct in the count, it will count as 4. So the John Frank and then the John Julie John Frank will count Frank twice. Okay. If this won't help either. So if we want to do distinct here, this will give us the same results because this distinct only applies to this table here and there's no duplicates. So I think there's maybe removes duplicate results, not the arguments of the count. So if we wanted to remove the arguments of the deduplicate those, then we should get each of them 3 times. So this will remove the duplicate count arguments. Okay.
Do we have to use lowercase for the?
No, I don't think so. No, you could use uppercase for those as well. I think in the style here, I was just putting them as functions in lowercase, but yeah, they could be uppercase as well. And these can be lowercase. These match and return things, so it can be lowercase as well. Okay, so within Cypher, we've kind of covered more or less the SQL style features. There's a bunch of other functions that we can get. There's so many functions that, you can, if you're looking for something, you'll probably get there. Just to briefly introduce one function, which I think is this one here. Yes, I got it right. We have a function for paths, which is pretty useful and interesting in the context of graph databases. So if we want to, for example, extract the length of the path, we can do that with length p. So we can find in this way the length of the shortest path without returning the path itself. Yeah. So if we're interested in the length of the shortest path, this would be sufficient. We don't need to do all shortest paths. We can just get whatever path and take its length. And in this case, it would be the shortest path between Frank and Julie that's directed, which would be 1, 2, 3, 3. Yeah. So we get length 3. So we're counting the number of edges that we traverse. Okay. So there's a bunch of other functions. This is just to give one example. So very briefly, because it's mainly syntax, but we can also update graphs. So we can create new nodes and relationships. We can delete nodes and relationships. We can detach or delete nodes. So detach, delete a node basically means it's like a cascade. It's delete a node and all of the relations it has, all of the edges it has. So delete everything related to that node. You can set to update labels and attributes. You can use remove to remove labels and attributes and so forth. So just to give some example or some flavor of what this looks like, because it's mostly syntactic, but this would create in Neo4j the session or the example we saw in the class, where we create the nodes, then we create the edges between those nodes, and then we drop all nodes and edges based on this this feature here. So match n, detach, delete n would essentially just delete all and detach all nodes, which would also delete all of the edges associated with that. Yeah, so it basically clears the graph. So yeah, we have some update language as well in order to create and delete and update and insert things into the graph. So that's the core part of Cypher, and that's the core part of Neo4j. So this is what will be the subject of the lab on Wednesday. We're going to look at Cypher. So again, Neo4j is a graph database. We have property graphs, we have Cypher. Just to mention very briefly, this scripting language called Gremlin, because it's also supported in a number of graph databases. Okay, license, we have open source for a single machine and commercial for a cluster machine. Just to mention for Cypher, so this is our Neo4j Cypher declarative query language. However, there's a number of graph databases that support a more procedural type query. So in this case, yeah, this is the query that we saw at the start where we were wondering what the results would be. Now we have the results, Julie, John, and Frank. So we're looking for people that Julie knows recursively who like a tag that Julie follows. Yeah, so Julie, John, and Frank, they all satisfy this. Yeah. We can do something similar using this gremlin language, which, as you can see, looks more procedural or more imperative in nature. It looks more like a scripting language. So essentially, what we're doing here is we've got our graph G, a reference to our graph, and then we've got a reference to the vertices in this graph. And then on these vertices, we can call this filter function in order to search the vertices for those who have first name Julie. And from that set of vertices, we can do the in vertex to find the vertices that go in. And then we can find out E to find the outgoing edges, nodes, and then we can loop that to do it recursively. And then we can essentially call this function to iterate over the results until there's no more results to do. Yeah. So I'm far from an expert in Gremlin. I don't think I've ever used it, but this is the idea. Yeah. So you have some sort of imperative language that allows you to do more programming language type style expressions over graphs. It's also Turing complete, so it's more expressive than Cypher, but harder to optimize, I would say. So that's Gremlin. So in general, Gremlin is somehow in between these two worlds in the sense that it's a way of specifying algorithms over graphs, maybe a little bit like what we saw with Giraffe, but it's also run within the graph database. So the graph databases can take this and optimize. For example, the graph database could interpret this g.v.filter first name Julie as a query and use an index to find the vertices that match rather than really reading them all. Yeah. So Gremlin. So have you heard of OLTP and OLAP before? So OLTP is online transaction processing. It means that essentially you're processing lots of small transactions, lots of queries that touch a small part of your database, lots of small inserts. For example, in a bank, you insert something that's a payment, or you look for the data for one client. OLAP is more this idea of online analytical processing, where you could be processing your entire data set to take an average of a column or to find out some sort of aggregate feature over a large part of your data to generate some sort of report or whatever it might be. So OLTP is this idea of like your typical relational database system, and OLAP goes more in the direction of something like Spark, where you want to analyze your entire data set. So yeah, Gremlin, it is claimed kind of sits between these two worlds. So it's something that can be run OLTP or can be run OLAP using something like Spark or Giraffe, for example. But okay. So that's Neo4j. That's our last class on NoSQL, also our last class overall on new topics in the course. We'll be continuing with the projects. Any questions, first of all, in this class? No? So we'll on Wednesday be looking at Neo4j in the lab. So we'll be giving you a database, a graph database in Neo4j and some questions, and you'll write the corresponding Cypher queries. So next week I won't be here. I have to travel. I have to go to Italy to teach at a summer school. But we'll organize project sessions. So we'll organize with Gabriele and Alberto to have something here where you can come and ask questions about projects, or maybe they'll do it on Discord. I'm not sure what, I think Gabriele started doing it on Discord. He said more people are on the Discord usually than in the room. So I'll leave it up to them to organize. So next week would be for projects, and then there will be a recess, and we'll continue afterwards with the projects and so forth. So you'll have some time dedicated to that. Yeah, some people were asking when the projects would be due. They will be due in week 14, I think on Wednesday or so. I published it. Yeah, so I published in 2 different days, so just so that you can focus on you're not doing two entregas at the same time. So the idea of that would be, it's kind of the latest more or less we can do it, because there's still the peer evaluation after that, and I don't want that to drag on into the exams. So I want that to be done before week 15. Okay, any questions in Zoom? All good. Okay, so see you on Wednesday.